One of the key concepts in thermodynamics is understanding energy flowing from one place to another. And we break that energy flow up into two terms. One which has to do with work, which is force acting over a distance, and the other is energy transfer in the form of heat. And heat is unfortunate because it's another one of those terms which we use in everyday life, but in thermodynamics has a very particular meaning. So in thermodynamics, heat is energy flow from high temperature to low temperature. So again, this is something everyone has experienced. You would not be surprised if you walked up to a hot pan on the stove and you put your hand on it and your hand was burned because the pan was at a high temperature and your hand is at a low temperature, and the energy would flow from high to low. On the other hand, there are lots of situations in which we can have energy flow, but we don't have any kind of temperature change. And in some situations we have energy flow, but the temperature does change. And as a result, if you look at the formulas that we write down for heat, there are a whole bunch of them. And it's always hard to know which one do I use and why are there so many. And the answer is because the heat depends upon the context. And you really want to break heat problems up into two pieces. There's either the problems in which the only thing that's happening is the temperature is changing, and then there are the problems where the temperature is never changing, but something else changes, like there's a phase transition or there's some chemistry. And then you can say, well, what if I have a terrible problem where there's chemistry and the temperature's changing? That's one of the beauties of thermodynamics, is we're always allowed to break things up into steps, and we can imagine first there's a temperature change step, and then there's a chemistry step. So let's imagine these two examples. What's an example of just a temperature change problem? For a temperature change problem, again, we don't want there to be any phase transitions, and we don't want there to be any chemical reactions. So imagine I had a big block of aluminum and it had some temperature, let's say 400 Kelvin. And I had another little block of aluminum that was, say, 300 Kelvin. And I brought the two of them in contact with one another. Now I would have a high temperature object at 400 K, a low temperature object at 300 K, and the energy would flow between them until they had the same temperature. On the other hand, you can have heat flow and you can have no temperature change. And that's because something else is going on. And that something else is either chemistry or it's a phase change. And because the chemistry is always hard to envision, it's easier for us to think about the phase change. So imagine I had a glass of ice water. It's at 0 degrees C. And now I'm going to flow some energy into that ice water in the form of heat. I can do that very easily by just grabbing the glass. And when I hold the glass, my hand is now warm. It's at body temperature, something 32 Celsius. And the glass is cold. It's at 0 degrees Celsius. So heat will flow from me into the glass. But the temperature of the water won't change. It's going to say 0 degrees C as long as it's a mixture of both solid water and liquid water. But the energy has to go somewhere, and the answer is the energy goes into melting the ice. So the longer I hold the glass, the more heat will flow, and the more ice will melt. And then finally I would get to a point where all the ice would melt, and then the temperature would start to raise, and now we'd be over in the other problem. So heat can either result in temperature change when there's no chemistry, no phase transitions, or we can have heat resulting in phase transitions or chemistry, but no temperature change. And if you have a situation that's both, break it into two parts. Solve the temperature change part, solve the chemistry part, and then put them all together.